All right, so let's start. So in the previous few classes, we were looking at this Efronstein inequality, which allows us to bound the variance of a function of n IID random variables. Right. So given any arbitrary function g, the variance of g of x1 through xn can be bounded in the following manner. Right, and that would perhaps allow one to derive, let's say, use the Chebyshev inequality to obtain a tail bound on g of x1 through xn. But as we know, the Chebyshev inequality would not be tight, particularly in the case when, let's say, g is just the sum of the n IID random variables. Right. So, and in fact, it is possible to derive a stronger tail bound, in fact, much stronger tail bounds, using McDermott's inequality and other similar inequalities. So McDermott's inequality essentially says that if g is such that changing one of the variables does not influence the value of the function g by too much, then we can in fact obtain an exponential tail bound on g of x, right? And in fact, it is possible to, with not much difficulty, one can strengthen this in the following manner. So this is basically the deviation when you change the value of just xi, right? But in fact, suppose that I have the following property. So in this case, effectively what I'm trying to use is that expectation of z minus zi prime square is less than or equal to some ci square, correct? But if instead I have expectation of z minus zi prime whole square when summed over, not expectation, z minus zi prime the whole square when summed over I equal to 1 to n is less than or equal to, let's say, some v square, okay, with probability 1. Okay, so here I'm not demanding that just with respect to one particular xi, the value of g differs only by an amount ci, right? This is a slightly more general form when compared to this, right? So this is basically saying that z minus zi prime absolute value is less than or equal to ci, right? And here I'm saying that the summation I equal to 1 to n z minus zi prime the whole square is less than or equal to v square. Okay, so in particular, it's possible that for some combinations of the xi's, you have small deviations, but for some other xj, the deviation is large. But overall, when summed over all of them, the overall deviation is somehow bounded by some v square. All right, so if this happens, then the probability that g of xn deviates from its expected value can be bounded as e to the minus t square divided by v square. All right, and this, for example, is helpful when we're in applications where, for example, you're looking at the largest eigenvalue of a random matrix. Okay, in these cases, we can't really say that this quantity is bounded by some particular ci. But instead we can say that the summation overall zi minus zi prime the whole square is less than or equal to b square. So both of them would effectively give you a bound if you tried this particular approach or this particular approach, but this would give you a slightly tighter.
Okay. Both are the same.
Which?
Yeah, sum of ci square is equal to b square.
Sum of ci square equal to b square.
Both should be same.
Correct. So this of course implies this, but let's suppose that I only know that summation I equal to 1 to n z minus zi prime the whole square is less than or equal to b square. But from this, I can't really say that, say, z minus zi, but perhaps I cannot derive a bound on just z minus zi prime. Right? Of course, I have the trivial bound that z minus zi square, z minus zi prime the whole square is less than or equal to b square. That's a trivial bound. But this would give me a much larger bound on z minus zi. So for example, this could be scaling with, this could be, say, linear in n. But if I try to derive a bound on an individual z minus zi prime, I would still end up with a bound that is linear in n. And that would not be particularly helpful. Okay, so again, I will not prove these results. So much of this is taken from the book by Boheron, Lugosi, and Massa, the concentration inequalities textbook, which is the link to which is put up in the course webpage. So you can look it up for the proof. But now what I want to do is discuss a few applications of the concentration inequalities that we've seen so far. Right? And towards the end of last class, I had introduced this problem of kernel density estimation, wherein you have x1 through xn, which are independent and identically distributed according to some unknown density fx. And the goal is to somehow get an estimate of fx. Correct? There are different ways of doing so, and one particular approach is to choose a smooth function k, which also satisfies the property that integral minus infinity to infinity k of x dx equal to 1, and k of x is greater than or equal to 0 for all x. So in other words, k of x is a density, it's a smooth density function. And we estimate fx using this particular approach. We take one Pn of x to be 1 over n times, so some scaling factor, times summation I equal to 1 to n k of x minus xi divided by hn. Okay, so if we just look at this, effectively what we are doing is, so think of, for example, k as, let's say, a Gaussian, right? Effectively what we're doing is taking scaled or linear combinations of k, right? You're effectively just shifting k and adding them up, depending on and how is the shift. So if I take a particular value of x1, then what is k of x minus x1 divided by hn? Assuming that k is, say, the standard normal. Correct. So it'll have mean xi. And what about the variance? It'll just be hn square, right? So this effectively, assuming that k is a zero mean random variable, this will have mean xi and variance equal to hn square. So if you think of estimating f using a sequence of, say, pulses or which is effectively what the Gaussian looks like roughly. Then Hn basically controls the width of this pulse, and xi essentially indicates the location of this particular pulse. Correct? Well, all right. So suppose that we use this particular estimator. How well does this estimator perform? So one way of measuring the performance of the estimator is using the L1 distance. Right? So the error could be measured in the following manner. So it is expectation integral minus infinity to plus infinity of fx of x minus Pn of x dx. Say for a given set of samples, the error is measured through the L1 distance. So of course, there is a corresponding average error. Let me call this. So this is a function of the n. So this phi n of x is in fact a function of n IID random variables. Correct? Each random variable is drawn according to fx. So let's assume that we want to derive a bound on this probability, the probability that the error is greater than the expected value plus some delta. Correct? Is it true that the error is decaying in n? Correct? That's what we want to find out. So how would we do this? I have g of x1 through xn to be integral from minus infinity to plus infinity fx of x minus Pn of x. And if I want to use, say, the Efronstein inequality or the McDermott's inequality, I have to show that changing one realization of xi does not influence this L1 error by much. So how would we do that? Let's take g of x1 through xn minus g of x1 xi minus 1 xi prime xi plus 1 to xn. Which is integral from minus infinity to plus infinity fx of x minus Pn of x minus fx of x minus Pn prime x, where this Pn prime is basically corresponds to the ith random variable replaced with xi prime. Right? What do you think we can do next? So just to build some intuition, let's look at Pn prime or P minus Pn prime. Changing, so Pn is basically a sum of functions of xi's, right? Just one particular pulse, right? And that should, intuitively, that should not influence the function by too much. Moreover, I know I have some nice properties for this particular pulse. correct? But then I have this integral of absolute value of something, right? So what can I do? So if I'm somehow able to get phi n minus phi n prime, I know that phi n minus phi n prime is not too large, but I don't have phi n minus phi n prime directly. Correct. Correct. So this is less than, or I claim that this is less than or equal to integral from minus infinity to plus infinity absolute value of fx of x minus pn of x minus fx of x minus pn prime of x dx. Is this okay? Do you all agree? Okay, so which means that the fx just cancels out, right? But now what is pn prime minus pn? So this is effectively equal to integral from minus infinity to plus infinity absolute value of pn prime of x minus pn of x dx, right? But what is this equal to? Correct. Exactly. So all except, well, one doesn't exactly appear twice. You have two different terms. So effectively you will get 1 by n times hn k of x minus xi divided by hn minus k of x minus xi prime divided by hn. Correct? Okay, can I get a bound for this particular quantity? Correct. So I can say that this is less than or equal to integral from minus infinity to plus infinity 1 by n times hn k of x minus xi divided by hn plus k of x minus xi divided by hn, where I'm basically using the property that mod of a minus b is less than or equal to mod a plus mod b, and k is anyway a non-negative function. Should be xi prime. But what is integral minus infinity to plus infinity 1 by n times hn of k of x minus xi divided by hn? It's yeah, overall that's going to be 2 divided by just n. So to see why that is the case, substitute y equal to x minus xi divided by hn. So dy equal to dx by hn. So this above quantity is less than or equal to integral from minus infinity to plus infinity 1 by n times k of y plus, okay, if I use a y prime for k of for x minus xi prime by hn, this k of y plus k of y prime dy just dy. Anyway, both of these are effectively the same, so this is equal to 2 times integral minus infinity to plus infinity, k of y is equal to 1. So this is just 2 divided by n. But now we don't really know what the error is. What is the expected value of this particular error, right? In principle, it could be large, but how large can it be?
Negative or whatever.
Phi n is, sorry?
Completely destructive period.
Okay. But can we use something much more loose? Correct, right? So the error or the let's look at the expected error. Or even the error itself. So the L1 error is integral from minus infinity to plus infinity of fx of x minus pn of x dx, but this is equal to, this is less than or equal to integral minus infinity to plus infinity fx of x plus pn of x dx, right? But what is integral minus infinity to plus infinity fx of x? It is 1 because fx is a valid PDF. And integral minus infinity to plus infinity pn of x dx. Yeah. That will also be 1 because it is 1 over n times summation of PDFs. So this is less than or equal to 2. So now if let's say I want to find what is the probability that the error. So what this also means is that the expected value of the error is at most 2. Correct? So let's say I want to find what is the probability that the error is greater than or equal to the expected value of the error times 1 plus delta. Let's say using Chebyshev's inequality. I have a bound on the variance, right? Because effectively here I'm saying that the variance is, so it's a bounded function, so it satisfies the bounded differences property. So what can I say about the variance itself? Let's maybe do that separately. I know that the expected value of the error is less than or equal to 2, but what can I say about the variance of the error? Using the Efron-Stein inequality. So each Ci is 2 by n.
Yes, sir.
1 by 4 times summation Ci square. Correct. So it's 1 by 4 times summation I equal to 1 to n ci square, and ci is just 2 by n. So this is less than or equal to 1 by n. Right? So it's summation 4 by n square. So it's 4 by n square times n times 1 by 4. So it is just 1 by n. Right? So if I now use the Chebyshev inequality, what is this less than or equal to? So it is 1 by so it's the variance divided by expected value of the error square times delta square. So it is 1 by delta square times n times so maybe some constant. All right. But in fact, we can do much better because we can use the McDermott's inequality to in fact get an exponential tail bound for this particular quantity. Right, but at the very least, just using the variance, we can derive a Chebyshev type inequality. Any questions so far? Sorry? Correct.
Should be 1 by n squared.
Why 1 by n square?
It's the normalized sigma square by t square.
Correct.
So
Good.
variance is less than equal to 1 by n.
Correct.
Should be less than 1 by n square.
Sigma square is the variance, right? So it's just 1 by. The variance sigma square is 1 by n. Sigma square by t square is 1 by delta square times 1 by n.
So these questions where you can actually find the bound of the variance, but not actually calculate the gain.
Correct.
And you perform an experiment,
Yes.
the last value.
Correct.
So that means that the value you get for your quantity
Correct.
is very close to the variance.
Correct. Exactly.
So you just get the mean.
You get the mean. Yes.
That's the proximate response.
True. Yes. But in some applications, it's still possible to derive a bound on the mean, in which case you know exactly how well you perform, or you can get a loose bound on the mean. Even if you don't know the exact value of the mean, if you are able to get, let's say, if you are able to show that the mean decays as, say, 1 over n, right, then it means that it's not just that the average error decays as n tends to infinity. With high probability, the overall error is also tends to n, whatever is less than 1 over n as n tends to infinity. Correct.
So the variance is exponentially, then you perform an experiment.
That's not enough. Sure, if you perform the experiment, then you can possibly estimate it, right? If you perform the experiment, but what the Efronstein inequality or these kinds of tail bounds allow you to say is effectively you're converting an average case result into a high probability result. So for example, if you can show that so in this case, if you can show that the average L1 error is small, then you're effectively here saying that with high probability, the error is going to be small, which is a stronger claim than just saying that the average error is small. Because if the average error is small, the deviation from the average error is also small with very high probability. In fact, with exponentially decaying probability of error, you'll be deviating from the mean by an amount greater than whatever error expected value times delta. right? So if, let's say, I'm able to say that the expected value of the error is, say, 1 over square root of n, or 1 over log n, or something like that, then the probability that the error is greater than, say, 2 times square root of n is less than or equal to e to the minus some delta square n, right? And that follows from McDermott's inequality. So originally we would have been only able to prove that the expected error is 1 over square root of n, correct? If we were able to derive a bound on the average L1 error. But now with very little effort, we are also able to say that with probability 1 minus e to the minus delta square n, the error is going to be less than or equal to 2 divided by square root of n.
So once you
Correct.
follows these patterns
Correct.
and you perform one experiment,
Sure.
high probability you will have
That is also okay. Yes.
So you have to do the experiment.
You don't necessarily have to. So if you're able to get a bound on the average value, you don't need to do the experiment. But suppose that you don't have any bound on the expected value, then sure, you can do the experiment, you would get it, and then you're guaranteed that with high probability you will be close to the expected value. So it's also a way to estimate the expected value, because you know that if you perform the experiment, you're going to be very close to it. Any other questions? All right. So let's look at this other problem, which is quite a fundamental problem in statistical learning theory. All right. So we look at the following problem of classification. In particular, binary classification, wherein you have an observable, let's call it X, and the corresponding class that it belongs to, which I denote by Y. So for example, think of classifying images, right? You want to know if there is a particular kind of an object in the image or not. That's a binary classification problem. Is there a vehicle in this particular image or not? Is there a cat in this image or not? Right? So these are binary classification problems. And in this case, X is your observable, so you can think of this as the image, and Y is the object. Present in this particular image. Right? So we'll assume that X is drawn from some particular set. Okay, with what set it is drawn from is not going to be particularly relevant. It could be finite, infinite, countable, uncountable. Let's not worry about that. But I will assume that Y is binary. So let's say 1 and -1 are the two classes. Maybe 1 denotes that the object is present and -1 denotes that the object is not present. Right? So we'll use the following general version, wherein we assume that X and Y are drawn from some joint distribution Pxy. Okay. So for example, in the object detection problem, in a particular image, given X, Y is fixed, right? So for a particular image, either there is a cat present or it's not present. So in fact, Y would be a function of X. But we'll allow for further generalization that Y could be a random variable which is conditionally dependent on X. So suppose that X and Y are jointly distributed according to Pxy. The goal of classification is to find some function which estimates Y from X. So the goal is to design a function G, which we call the classifier, which estimates whether the object is present or absent in given the image. Correct? Now, so how do we find whether a particular classifier is good or bad? We need some kind of a metric, right, to evaluate the performance of a given classifier. And one common way of evaluating this is what is the probability that the classifier gets it right, classifies correctly. So the probability that g of x is not equal to y. So we call this the risk for a particular classifier G. Now you could these things can be generalized. So in general, the risk for a particular estimator or classifier is typically taken to be the expected value of some particular loss function between g of x and y. So in this case, if I take this to be the risk, then what is the loss function? If I had to write this particular risk as an expected value of some loss function, what would that loss function be? So it would just be the indicator, expected value, indicator of g of x not equal to y. So this is equal to 1 if g of x is not equal to y, and 0 if g of x equal to y. So this is what we call the risk. And the goal is to somehow design a classifier that minimizes this risk. Correct? So suppose that we knew what pxy is. Then what would be the function g that minimizes the risk? Correct. So in fact, that would be the map estimator, or effectively the conditional expectation. So G star is in fact equal to R max of P y given x, y given x. So if you, for example, if you go back to your digital communications course, you can think of this as one way of interpreting this is that y is basically, you can think of y as a BPSK symbol that is transmitted through a channel. The channel could be much more general, and the goal is, so y is what is being transmitted in this particular case, and x is what is observed at the output of the channel, and you want to estimate what was transmitted given what you have received. And the best possible detector or demodulator is the map detector, which is the argmax of P y given x of y given. So this is the map estimate. So this is all well and good, but in most applications of interest, we don't know what PXY is. In the special case of, let's say, digital communications, we know that we have a model for the channel, in which case we can design the map estimator. But in most problems of statistical learning, we don't know what PY given X is. What we are instead given are a bunch of samples drawn from this distribution. Let's suppose that we're given n samples, all drawn IID according to PXY. So this is our data set. Right, so it's a supervised learning problem where we're given a bunch of samples drawn according to the correct distribution, and our goal is to estimate G or find G which minimizes whatever the risk. Right? And one way to obtain such a G is, well, ultimately the goal is to minimize this average risk. Right? We can't compute the average risk anymore, but we can estimate this particular average risk using the n samples. Right? So we can compute the empirical risk for a given G. So I'll define our G of whatever. You should view this, you should think of this as a result of the samples. It's a function of the samples. This is equal to 1 over n summation I equal to 1 to n G of xi not equal to yi. So on what fraction of the samples does my G get the estimate wrong? So this is just the fraction of the time that the prediction is incorrect. And this quantity is called the empirical risk. So one way to design a classifier is to find a G that minimizes this empirical risk. So I'll call this Gn, which is the argmin overall G taken over some class of functions script G, right, of the empirical risk. So given these samples, I have this particular empirical risk, and I try to find the function G which minimizes this particular risk. So for example, if I'm trying to perform empirical risk minimization over, let's say, a class of 2-layer neural networks, feed-forward neural networks, then effectively I'm taking the argmin over all possible weights of the neural network of the empirical risk. Right? And let's assume that I'm able to solve this optimization. Okay. In practice, just solving that optimization problem is not very easy. So you need to come up with algorithms to do it efficiently. but for now, let's not assume about efficiency. Right? And let's assume that we're able to do this, perform this optimization algorithm exactly. So this gives us some particular Gn, correct? But one thing to keep in mind is that this depends on the n samples, and this could potentially be different from the expected value. Correct? After all, the goal was to minimize the expected risk, which could be different from the empirical risk. Right? But then what do we know about the empirical risk itself? So let me look at R of Gn. Let me use a slightly different notation for this. I will call this R subscript n of G. Okay, so R subscript n basically denotes empirical risk taken over n samples, whereas R effectively denotes the expected risk. Okay, and I want to find R of Gn. Remember that Gn is obtained by minimizing the expected, minimizing the empirical risk. R subscript n of G. So first, let me try to estimate R of Gn minus R of G. How far can the risk be different from the empirical risk? Try to do this particular R of G minus Rn of G. Sorry? Why 1? Sure, but can I say something more? So again, this is, recall that this is equal to expected value of the risk. So this is expected value indicator G of x minus not equal to y minus 1 over n summation I equal to n indicator G of xi not equal to yi. Right? So sure, it's maybe upper bounded by 1, but then can I derive a probability bound for this? What is the expected value of the empirical risk? Correct, right? So we know that expected value of Rn of G equals R of G. Right? You all agree with this. So I can try to derive a tail bound on this particular, on the probability that this deviates by an amount greater than delta. Right? But what kind of a variable is Rn of G? Recall Rn of G is 1 over n summation I equal to 1 to n indicator G of xi not equal to yi. And so Rn of G is a random variable. It's a function of n IID random variables, whereas R of G is a number, right? Its expected value over pxy of indicator g of x not equal to y, which is the same as saying the probability that g of x is not equal to y. Correct? So what kind of a function is Rn of g? It's a sum of n IID Bernoulli random variables, right? So I can just use Chernoff one. So what can I say about the probability that Rn of g minus R of g is greater than or equal to delta? Let me use epsilon here. What is the tail bound? If you want, you can say greater than epsilon times R of g.
Constant epsilon square.
Some constant times epsilon square times n, right? Constant times epsilon square R of g times n, because it's in the multiplicative form. All right. Well, so that is great, right? So we know that on average, the empirical risk is going to be very close to the expected risk. But we have to be a little careful here. What we want to find is how close is the empirical risk to the expected risk for Gn, right? In this case, this is for a fixed G, correct? For a fixed function G. But what we really want is, let us say, how far is Rn of Gn when compared to, let's say, R of G star. So this is the optimal risk that I can possibly obtain using the best possible G star. But this Rn of Gn is not that simple, right? Because Gn itself is a function of the n random variables. It's not a fixed function anymore, right? This is equal to the arg min for all possible G summation I equal to 1 to n G of xi is not equal to yi. Correct? So this Rn of Gn is no longer just a summation of IID Bernoulli random variables. It's a minimum of a summation of IID random variables minimized over a certain function class. Correct? So for this particular quantity, I can't really use a simple Chernoff type of. Do you see why that is the case? So this is a function uh, let me call it, say z. This is a function of g, xn, and yn. For a given g, this is a sum of IID random variables, correct? But what I have is the minimum of these functions. So you can think of this as a random process, right? For each g, I have a random variable, correct? And I'm taking the minimum of this particular process. And the minimum is no longer just a simple sum of random variables. I cannot express it as a sum of IID random variables. So give it some thought. Let's stop here.